In this paper, we present an optimization-based approach to automate the process of adapting mixed reality interface layouts to different environments. Our model extends upon past work by considering and maintaining the semantic associations between virtual interface elements and the physical environment, as illustrated here using the purple lines. Mixed reality holds the promise to transform how we interact with digital information. Unlike traditional screen-based devices, applications in mixed reality can be directly embedded within the real world. One current limitation of mixed reality, as a result, is that when users move between environments, they have to manually adjust their previous layouts. This is a highly tedious and time-consuming task, especially considering that this must be performed every time users change their task or environment. Existing solutions adapted mixed reality interfaces based on visibility, environment geometry, and observed user behavior. We believe the semantic associations between virtual interface elements and the physical environment are equally important to consider. For example, a potentially sensible design decision might be to place a calendar application next to a physical clock because they share semantic associations with time. We might also place a music streaming application on top of a pair of headphones because they share semantic associations with sound. Our approach takes as input a scanned mesh of the user's environment with relevant physical objects and usable spaces labeled, and a set of virtual interface elements with predefined values representing their utility for the current task, their usage requirements, and their semantic associations. We voxelize the labeled spaces and volumes into potential containers for our virtual interface elements. Based on these inputs, we formulate the adaptation process into a linear program that optimizes for 6 objectives. Our model's first objective is to generate a layout that spatially reflects the semantic associations between virtual interface elements and objects within the physical environment. As you can see here, in our model-adapted layout, the PDF reader is anchored to a stack of paper due to their shared semantic associations with reading, writing, and paper. A music application is placed next to a pair of headphones for a similar reason. Here we make a few adjustments and use our model to adapt the new layout to another environment. We ensure our model's behavior when we set it to avoid placements around anything associated with people. Notice how all the elements have been shifted to the left. Second, we take into account the usefulness or utility of each element with respect to the user's current task. For example, while a user is working, they may have the following applications from most useful to least useful open: a PDF reader, a messenger application, and a music streamer. Our model will prioritize the placement of high-utility elements in accessible locations, as we see here in the adapted layout. Our model further considers the requirements of each virtual element. Specifically, for each element, we consider the extent to which it must be visible, whether it requires touch interaction, and its tolerance for background complexity. Fourth, our model biases the placement of virtual interface elements in rows and columns to produce a layout with more structure. Fifth, to reflect how user work practices are sometimes environment invariant, we introduce a between layout similarity metric as a trade-off in our model. Last, our model minimizes the number of occlusions between interface elements to maximize the overall visibility of the layout. In the following, we demonstrate the versatility of our model with several example application scenarios. First, we use our optimization model to create a portable office. The applications are laid out to fit a typical desk worker scenario and include applications like a PDF reader, search engine, and word processor. The portable office is now automatically adapted to a meeting room. We see several virtual interface elements particularly influenced by semantic associations. For example, the placement of the word processor next to a stack of paper. Second, we create a mixed reality layout for casually browsing social media contents. This setup includes a few central elements placed in a row and a bunch of less important applications placed in the user's periphery. When we adapt the layout from our bedroom environment to a coffee shop, the main applications are kept in the same central location. The periphery applications are shifted to the side due to spatial constraints. We created a mixed reality layout suitable for travel planning. It contains several relevant applications such as a hotel booking website, a travel website on a garden, and several image browsers. The layout is adapted from the user's dining room to their kitchen. Here we see a significant number of semantic associations formed. The garden website was, for instance, anchored to a plant. Likewise, images of food were placed either next to the snack container or the refrigerator. The placement of the applications becomes highly coupled with the semantic context, thus we believe highly memorable and predictable after brief usage periods. We evaluated our model against a baseline that does not consider semantic associations. We found that our optimization model decreases the number of interactions required to build a satisfactory interface by 33%. In conclusion, we contribute an optimization-based approach to adapt mixed reality layouts between different environments. We believe our work is a further step forward in enabling mixed reality interfaces to be truly responsive to the context of use.